So, hello everyone. Last class I was discussing about the residual stress measurement technique by destructive technique. Today I am going to deliver a lecture on residual stress measurement by non-destructive technique, that is called NDT technique. So, here this is the today's lecture content, that means measurement by ultrasonic method, measurement by diffraction technique, and also I will discuss what are the different steps generally followed in thermomechanical analysis to predict residual stress in a weldment. That related thing also I will discuss. So, first of all I will discuss about measurement by ultrasonic method. All of you are well familiar with ultrasonic method, then also I should tell what actually it does, that I am going to briefing here. So, ultrasonic method is a NDT types of residual stress measurement techniques, which are based on acoustic elastic, or you can say acoustic elasticity effect. So, according to this measurement technique, the velocity of the elastic wave propagation in a solid is dependent on the mechanical stress. That means, once a elastic wave propagate in a solids, this propagation of this elastic wave is dependent on mechanical stress. So, the characteristics of this elastic wave change once inside the solid, there will be some residual stress. This you should keep it in mind. So, in this methods waves are transmitted by a transducer which propagate through a region of material and are dictated by a receiving transducer. Here I am just showing how it happens actually. So, there can be different types of configuration of ultrasonic measurement technique. Here I have shown, like through thickness we can do the measurement by a pulse echo, which is called through thickness pulse echo generally. Here one thing you should keep it in mind, this ultrasonic wave generally can propagate through the solids. One, there will be some vacuum space, then what happens, it can pass through that. So, here this ultrasonic wave once there will be solids, then only through this solid it will propagate. So, once there will be some vacuum or open space, from there it will rebound back. So, this is generally a transducer, you can see in figure 1. So, here by using pulse echo, so we can measure through thickness what is the pattern of residual stress distribution. This is another example of through thickness by pitch echo. So, this first one is called pulse echo and the second one is called pitch echo. So, pitch echo generally have inclined propagation through the solid, and it is also inclined receiver, that means inclined receiving transducer which receive the sense of this what it is called ultrasonic wave. So, by analyzing this receiving data, we can say what types of residual stress distribution through the solid is there. This is another example, we can predict the residual stress distribution near the surface region also. So, by using surface piece cast, here this is the delivering transducer and this is the receiving transducer. So, once we deliver a ultrasonic wave through this surface which is horizontal to the surface, this we can receive by another transducer. From there whatever the resolution we got, that resolution we can analyze and predict the residual stress distribution and that weldment. Now, this technique is effective for analysis of residual stress in interior of the material, what I have told you. So, we can measure this through thickness residual stress distribution by this technique. It has lot of advantages, like what happens by this method we can measure the residual stress distribution through thickness. That means, whatever the depth of measurement we can do, that cannot be done by X-ray diffraction techniques. That is another important residual stress measurement technique. So, here depth of measurement generally is higher than that of X-ray method. This method generally is a very quick method, it is a inexpensive method and it is portable, free of radiation, because here there is nothing related to radiation types of phenomenon. Okay. One of the disadvantage of this ultrasonic method is its resolution is little bit low in nature. Now, I will discuss another non-destructive residual stress measurement techniques, especially by X-ray diffraction techniques and Neutron diffraction techniques. So, first of all I will discuss about X-ray diffraction method. X-ray diffraction technique generally measure the residual stress by measuring the strain. So, it is not measuring the stress directly, this you should keep it in mind. First of all, it is measure the strain through the lattice structure. So, from their lattice structure whatever the strain they measured, by using that things we can predict how much residual stress is present in that specimen. Okay. So, this method generally elegantly takes the advantage of crystalline structure of the material itself. That means, by using the atomic lattice spacing as a strain gauge. So, what happens here in this types of method, here a X-ray generally propagate through the lattice plane. Then what happens, due to diffraction of that X-ray, we measure this lattice spacing distance, that means layer to layer distance, or you can say atomic layer spacing distance. Let us this is one atomic layer, this is another atomic layer. So, what happens, by measuring this atomic layer spacing distance, you can say, that means from here to here, we can easily predict the how much residual stress available in the specimen. How it is, little bit I will discuss in detail in subsequent slides. Then also I should tell, first of all we have to predict the we have to predict this D spacing in a sample where there is no residual stress. After that we have to predict this D spacing with a sample where there is residual stress. So, from the comparison of these two, we can easily predict actually what is the value of residual stress available in that specimen. So, here one thing you should keep it in mind, here this lattice spacing, this atomic lattice spacing, this is generally act as a strain gauge, this you should keep it in mind. So, here generally this atomic lattice spacing act as a strain gauge. For that reason, as a result, thousands of built-in strain gauges within the crystal are available for strain measurement by this method, that we can say. So, here I have written, that means this lattice spacing here act as a strain gauge, because if the lattice structure subjected to any types of residual stress, then this lattice spacing varies. So, this varying lattice spacing can give us the concept of residual stress distribution pattern. Okay. That is why here we consider, we called this lattice spacing is a built-in types of strain gauge. So, we have taken this advantage of this built-in strain gauge in X-ray diffraction techniques. So, here the strain present can be determined by the measurement of elastic atomic lattice spacing, what I have told you, that means by measuring the D spacing, this elastic atomic lattice spacing, what I have told you, this is the layer to layer distance of atomic layer to layer distance, you can say. This is also sometimes called D spacing, which is commonly used, because this distance between these two layers is called D spacing. So, this lattice spacing is the distance between the plane of the atoms, which is dependent upon the material and stress present in the material, what I have already told you. So, without a stress present in the material, it will have one types of D. If there is some stress present, it will have some other value of D. This you should keep it in mind. So, for a given X-ray wavelength, because once we pass through this lattice some X-ray, then for a given X-ray wavelength, let us say X-ray have a wavelength lambda, then there is a relationship between this X-ray wavelength lambda with this D spacing. This is developed by a scientist whose name is Brack. So, based on these things, this is called Brack spacing, Brack's law. This is called Brack's law. So, this Brack's law states that this n lambda equal to your 2D sin theta. This D sin theta, what is this D? D is the spacing between two, you can say, atomic lattice layer, and theta is the angle between horizontal plane or you with X-ray, or you can say incident angle. So, theta is called incident angle with horizontal plane, that also I will show you in subsequent slide. So, here one thing you should keep it in mind, this X-ray diffraction to occur, that means to occur this X-ray diffraction, here constructive types of wave interference is required. You can say that this diffraction can be categorized into two different categories. One is called constructive, another one is called destructive types of what it is called interference. So, in destructive types of interference, here generally if the wave length of two wave is same, and if it is in opposite phase, then what happens in destructive types of interface, it will be vanish actually, we will not get any output actually, this you can say. But if in case of constructive types of wave interference, if the wavelength is same of two X-ray wave, and if it is in same phase, then what happens, there will be generally summation of these two wavelength will be there. So, that means superimposed principle we can use there. So, there we can get a means highly resolution types of output, what I am telling, understand. That is why here it is written, for a X-ray diffraction to occur, constructive wave interference is required. And another things, the path difference traveled by diffracted beam through the material as compared to non-diffracted beam must be equal to n lambda. What does it means? Now, I am going to discuss in detail what is this path difference. Now, I am going to explain this in detail. So, first of all we should know what is diffraction. So, we can say diffraction is bending of light, or you can say electromagnetic wave around any sharp corner. So, this can be X-ray, it can be electromagnetic wave, this can be light also. Okay. So, once it fall in any sharp corner, there is a bending of light occur. So, that phenomena is called diffraction. Now, I am going to discuss about Brack's law. So, now I am going to discuss about Brack's law and how to use this Brack's law to find out this atomic layer spacing. So, this is one layer, this is another layer, atomic layer actually. Now, let us from a source, we are from a source, let us the X-ray is coming or falling in this lattice plane, and this top lattice plane have a reflection, or you can say diffraction like this, and this bottom one have a refraction like this. Okay. So, let this is X-ray 1, this is X-ray 2, and this we are receiving by a receiver. That means, this is the detector we can say. Now, the distance between two layer is called D spacing, or you can say atomic layer spacing, that you can say. Now, you can see. So, what I told, that means to occur the what it is called X-ray types of diffraction and detected by some detector, it should be constructive types of interference. So, little bit about this, what is this constructive one and what is the destructive types of diffraction. Constructive means, let us two wavelength which are in same phase. In case of constructive, this final resultant wavelength, once this combined together, we will get the constructive types of diffraction, which is the superimposition, or you can say summation of this two wave. This is called constructive types of diffraction. Constructive types of diffraction. For destructive types of diffraction, there are two wavelength which are opposite in phase. So, in this case you see, once we superimpose this thing, this will nullify. So, here it is called destructive types of diffraction. So, I am not going in details about the discussion of all the thing, I am just showing here how to find out this D spacing. Now, you see, let this is one X-ray which is fall top surface, and its top surface, let the position is here, this I am representing, this position is C, this is E. Okay. Let us from here, this is the source position of this X-ray 2, this is B, this is actually C, this is I am representing another words, these are all another word, let us A, B, C, let B, C, D, E, let this is your F. Now, if I draw a perpendicular with this second wave, then here I will get, let us this position, position cut this second wave at a location, let this location name is M. Okay. Now, if I draw another perpendicular here in this second wave, then here I will get, let this is your N. Okay. Now, here let us consider the incident angle of this X-ray is theta, this is also theta. Now, we have to find out this d. So, here you see this first wave, here you can say this B c is equal to A m. Similarly, we can say C d equal to your N f. So, here you see the second wave travels some extra path, you can say second wave of X-ray travels some extra path. So, this path difference of this two wave, we can write path difference of this two wave, path difference of this two wave will be your m e plus E n, that we can write, correct, m e plus E n. So, this we are interested to find out what is m e plus E n. So, if this is theta, then we can say this will be 90 degree minus theta. So, this will be 90 minus theta. So, this is also will be theta. So, if again if this will be theta, so this also will be theta, correct, this also will be theta. So, here by using the concept of triangle, so here you see this is perpendicular, this is also perpendicular. Okay. Now, by concept of this perpendicular triangle, we can write from this triangle delta, that means triangle CME, from triangle CME we can get that means sin theta will be equal to your equal to your ME divided by CE. So, you know this CE is equal to here I am writing C is equal to our ds spacing, correct. So, once we know this C equal to ds spacing, then sin theta will be your ME by d, this we can get. So, from here we can get ME is equal to your d sin theta, correct. So, now from another triangle, from triangle CEN, what we can get, sin theta we can write as En divided by CE. So, from here we can easily get En is equal to CE is already d sin theta. So, here path difference how much we are getting. So, from here we can say path difference is equal to your ME plus En, this will be equal to your 2 d sin theta, because this is sin theta, d sin theta, this is also d sin theta. So, this will give us 2 d sin theta. Now, how this 2 d sin theta is equal to your what it is called n lambda, this also you should know. So, to get this idea, what are the thing required to do? Let us the wave of 2 X-ray 1 which are coming like this, let us which are coming like this, both are in same phase, both are in same phase, both are in same phase. So, the first wave will just reflect like this, because it is not passing through this what it is called lattice, but here you see, but second wave is passing through this lattice spacing, correct. So, that is why there is some path difference. Now, here one thing keep it in mind, here why the crystal diffract this X-ray, this you should keep it in mind, there that is why here I am writing a statement, the crystal can diffract X-ray. So, the crystal diffracts the X-ray why the crystal refract the X-ray? Because the interplanar spacing, because the interplanar spacing that is D spacing, you can say interplanar spacing in a crystal lattice, always keep this thing in mind. Crystal lattice is of the order of that of wavelength of X-ray. Order of the X-ray's wavelength. This you should keep it in mind. That means, if the wavelength of X-ray is lambda, then this D spacing, you see this D spacing should be within the border of n lambda. That means, it can be 1 times of this lambda, or it can be 2 times of this lambda, or 3 times of this lambda. Now, you see, so to get this X-ray refraction, what I have told you, and to get the detection of this X-ray by detector, both the X-ray should have in same phase, correct. So, this output X-ray also should have in same phase with this first X-ray, correct. Then only here it will be constructive types of diffraction result, correct. Then only here it will be constructive, because if it will be opposite, your diffraction wave will not be detected by the detector. That means, destructive types of things, X-ray same wavelength, it will be vanish. So, in case of destructive types of diffraction, that is why you see, to get these things here, generally what should be this pattern. So, here you see, so this should pass through like this, after that generally it should pass through like this, correct. Then only what happens, so it can this whatever the things it is going, so it can go in this light spacing either by this, what I am telling, understand, or also I have told you inside this line spacing generally. So, that is why you see, to get these things here either will be a half wave, or here can be in between this emit distance, there can be 2 of this wave, if this spacing is what it is called different. But what happens, it will not be, because I have already told you crystal diffract, because X-ray wavelength is within the same order of lattice spacing, what it is called lattice spacing distance. What I am telling, understand, that you should keep it in mind. So, crystal diffract the X-ray because the interplanar spacing in a crystal lattice is of the order of the X-ray wavelength. So, whatever the interlayer spacing distance are there, this distance generally is on the order of what it is called, is on the order of what, X-ray. So, order of X-ray means it can be 2 times of this X-ray, it can be 1 times of this X-ray wavelength, it can be what, depending upon the type of material it can be, but it should be order of that X-ray wavelength. That is why you see, so we are getting the spacing, D spacing is 2D sin theta. So, this should be equal to your n into lambda, what I am telling, understand, where the lambda is the wavelength of the what it is called X-ray. This you should keep it in mind. So, how it is coming, I think you got this idea and it is clear to you. So, by this method generally we can easily find out what is this D spacing. So, D will be your n lambda by sin theta, correct, n lambda by sin theta. This you just keep it in mind, because this is very much essential for knowing how to find out this D, because this is the principle which we use to find out the what is called lattice strain, because this D we are finding out without a stress specimen and with a stress specimen. After that we differentiate, then by differentiating this thing we can find out a strain, and there is a relationship between stress and strain. For this by using that formula we can easily find out the stress value. So, that I am going to show. let us the stress free specimen have a d spacing is d0 and let us say stress specimen have a d spacing is di. So, once we know this di and d0, we can easily find out what is the elastic strain. So, this elastic strain between this or you can say two lattice layer is two lattice plane layer, it will be your di by d0 divided by d. So, this is the strain due to residual stress present inside the specimen. So, once we know this strain, then we can easily be able to find out the stress value. So, for that there is a relationship is there. So, this is the strain, you can say this is the strain. With this strain we know, with this strain once we multiply by a elastic constant, that means which is equivalent to Young modulus, you can say. So, that thing is here it is given like E by 1 plus lambda, this E by 1 plus lambda, this is the I am not going to derive this relationship, because what happens once I go for deriving this relationship, it will take lot of time, that is why I am not going to derive this thing. So, this E by 1 plus lambda is called X-ray elastic constant, it is called X-ray, which I have already written here, X-ray elastic constant, okay, elastic constant. And what is this psi? So, psi also I have written, psi is the angle subtended by bisector of the incident and diffracted beam and the surface normal. Let this is a plane, this is a incident ray, this is the diffracted ray. So, incident ray, diffracted ray, in this plane if we draw a bisector, okay, then whatever the angle we are getting, that is called psi. This you should keep it in mind. Okay. Now, by using this relationship we can easily be able to find out stress residual stress present in the specimen. Okay. This technique generally give the residual stress distribution near the surface region. So, wherever its fall this X-ray, that is why it generally give the means residual stress distribution over the surface region only. This surface region means within a range of 2 to 50 micrometer distance it can measure the residual stress distribution. Okay. But more than that thickness we should use some other technique, that also I will discuss. So, this measurement of residual stress by X-ray diffraction techniques is categorized into two different categories. One is called a single exposure techniques, that is in abbreviation like ACT technique, that is single exposure techniques. In this single exposure technique, here generally this tilt angle is this psi, generally use only one psi tilt angle is used, that is why it is called single exposure technique. Whereas, there is another technique that is called multiple exposure techniques, where generally multiple psi tilt is used over there. Okay. So, from there by using multiple psi tilt, that means at different orientation of this psi, we measure the stress, from there we can predict the overall residual stress distribution in case of multiple exposure techniques. But this single exposure technique generally is used for quick and efficient distribution of stress in a lattice specimen, or you can in a specimen. That means, this technique gives the user a very quick and efficient method to perform a stress measurement, whereas the MAT method generally that is called the multiple exposure technique is more revealing for material, but it takes longer time than ACT, because in ACT we are using only one single tilt psi, but here we are use multiple tilt psi. This you can keep it in mind. Okay. That is why definitely it will take, the second one will take more time, but it gives more accurate results, this you can say. Now, X-ray diffraction technique, here you see there are different types of widely applicable X-ray diffraction types of machine are available, like one is called position sensitive scintillation detector, PSSD you can say. This is based on X-ray diffractometer. Okay. This is generally this PSSD is based on X-ray diffractometer. There is another equipment which is used for X-ray measurement, that is called stress X-ray diffractometer. These are the equipment generally widely used for residual stress measurement, What I have already told you, this X-ray residual stress measurement technique generally measure the stress within a range of 2 to 50 micrometer distance from the surface. But for interior surface residual stress measurement, what we have to do? We have to generally cut the layer and we have to polish it very preciously, that is called electro polishing is required to do before measuring by using X-ray XRD technique. So, that is why subsurface and internal stress cannot be measured non-destructively, this you should keep it in mind. So, subsurface and internal stress cannot be measured non-destructively, because for internal or subsurface stress measurement we have to section it and we have to polish it, after that only we can get the stress distribution over there. Now, to measure this internal stress with X-ray diffraction technique, the weldment must be systemic, here you have seen the weldment must be systematically sectioned and surface to be measured must be electro polished, which I have already written. That is why destruction of that specimen is required to measure internal or subsurface residual stress by using XRD technique. Now, we will discuss about measurement by another diffraction technique, that is called neutron diffraction. Now, before going to discuss about neutron diffraction technique, first of all we should know what are the different sources generally available in neutron diffraction process. There are generally two different neutron sources are available. One is called fission neutron source, another one is called spallation types of neutron source. Okay. So, this fission generally is a continuous source, whereas this spallation source is generally is a pulse types of source. Okay. This fission types of source predominantly it is used generally in a steady state nuclear reactor. In fission types of technique, generally a monochromatic beam, here you see a monochromatic beam of neutron is produced by using a monochromatic device. So, a monochromatic beam generally is generated, that means in case of fission types of neutron source, but in case of spallation types of neutron source, you see the neutron beam usually consists a series of short pulse, this you should keep it in mind. So, this is pulse containing a spectrum of wavelength. So, it is a consist of a spectrum of wavelength, where in case of fission there is used a single wavelength of neutron source. Now, here I am going to discuss what is the principle of this neutron diffraction techniques. Here generally the principle which is used here, that is generally based on Debye-Sisser's cone. What is this Debye-Sisser's cone? That little bit I will brief here, then it will be clear to you, because I will not go in details about what is basics of this all neutron diffraction techniques, because you see then it will take lot of time. That is why here I will explain the concept of basic concept of this neutron diffraction residual stress measurement technique. So, the principle of this technique is, when a monochromatic radiation fall on a sample, then the diffraction from a generally Brack plane result in the form of a cone. You see, let this is a Brack plane. So, let this is a monochromatic incident neutron ray, let us fall in this Brack plane, then what happens after diffraction, whatever the shape of this diffracting beam is occur, this is shaped like a cone. So, it is a 3-dimensional types of cone actually, once is passed through this Brack's plane, or you can say once is passed through the material, then it's this output response is makes a cone types of shape. This cone have different types of what it is called resolution throughout the entire cone face in the sense for front you can say. So, here you will get different types of intensity. So, from this intensity we can easily be able to measure the residual stress distribution pattern on the specimen. How it is? Because if this plane or if this specimen contain a residual stress, it will provide a DS cone. DS cone means called Debye-Sisser's cone. D stand for Debye and S represents scissors, which I have written here already, and this is the Debye-Sisser's cone. So, what happens once it is a stress free specimen, it will provide some different DS cone, and if it is a stress specimen, it will provide some another what it is called DS cone. So, by comparing these two we can easily be able to find out what is the residual stress distribution pattern inside this specimen. So, we here this cone which makes a angle 2 theta with this horizontal axis, this you should keep it in mind. That means, the angle between this incident ray, you can say this is the incident ray with this diffracted ray, it makes angle 2 theta, which I have written at the end of this slide, you can say that I will tell. Okay. So, this diffracted beam generally is shaped using a suitable optical device. This we can shape by using a suitable optical device. The intensity profile is recorded as a circle on 2-dimensional detector. What I have told you, generally here we used a 2-dimensional types of plane. Okay. So, in this 2-dimensional plane we can record the intensity profile in this plane. Now, this techniques is capable of measuring internal stress without destroying the weldment, because in previous case X-ray diffraction techniques is generally can measure the surface near the surface, actually we can say within a range of 2 to 50 micron meter thickness layers residual stress by X-ray diffraction technique. But in these techniques we can measure through thickness residual stress distribution also. How it is, that I am just showing, because this technique, that is why here I have written this technique is capable of measuring internal stress without destroying the weldment. So, neutron penetrate several inches, here I have written inches of metal, and it can be diffracted from the internal volume of metal weldment to measure the internal residual stress. Okay. So, it can penetrate several inches, what I am telling, understand. Now, this optical resolution and 3D map can be obtained, what I have already told you. In a 2D plane we can find out this optical resolution, and also we can find the 3D map of this output, from where we can predict the residual stress distribution. But here one thing you should keep it in mind, this technique is very expensive. Okay. Very expensive means some crore rupees, this you can say. Okay. So, here what is this theta? Theta is the generally angle between the incident beam and the D planes, whereas 2 theta is the angle between incident and diffracted beam. Let us here the incident beam is this, that means horizontal line, and after diffraction whatever this is the diffracted beam. So, in this case this angle is called 2 theta angle, this you should keep it in mind. So, this is the basic concept of this Neutron diffraction technique. So, by analyzing this outcome resolution, you can say, or you can say outcome intensity profile, we can predict the residual stress distribution inside the pattern. So, I am not going in further details on this. Okay. Now, I will discuss about the numerical analysis of residual stress measurement. Okay. That means, how to use numerical method to analyze the residual stress distribution. So, here I am going to discuss briefly what are the different steps generally we used to follow to measure or calculate or predict the residual stress distribution by using some numerical techniques. So, let us this numerical techniques we are going to use is finite element technique, FEM method. Okay. That means, FEM technique, that is FEM represent finite element method. Okay. So, or you can say sometime it is called FEA, finite element analysis techniques. Okay. So, this is an approximate method. How it is, that I am going to discuss here. So, first of all we have to define the geometry. So, first of all we have to define the geometry in which we generally going to analyze the stress distribution. Okay. So, we have to first define this geometry, or you can say that is called modeling. After that, in finite element method means here the finite number of element or finite number of division is required to make in that structure, okay, or in that model. So, that is called generally, that technique is called meshing technique. Meshing means let us, this is our plate, this is our plate. So, in this plate, let us, here we are interested to do the welding, interested to do the welding. So, first of all we have to model this full geometry, that is called modeling. Okay. That is called modeling. Here we are interested to do the welding. Okay. Let us, now after that we have to generally discretize, that means we have to divide this geometry into number of division. number of different division. But here one thing you should keep it in mind, here you can optimize the this number of division, because that is called mesh sensitivity analysis. We were going to do actual prediction of the output. First of all, we have to optimize this discretization or meshing, that is called mesh sensitivity analysis. Okay, for that different technique is there. So, generally from very coarse mesh to gradually we have to go for fine mesh. So, at a particular mesh, after that generally the error percentage significantly reduced. So, from that location you can decide your optimum discretization. That means, you have to start from a very big division and you have to gradually decrease it to a small division. After sometimes you will get a number of division for which you will get optimum result. That means, after further discretization, after further finding of that division, if it will not affect more, then you can take that division, that is called optimum division, or you can say that is called mesh sensitivity analysis. So, first of all we have to measure the thing. So, before generally meshing itself, we have to define the material properties. So, first of all we have to do the modeling, then we have to put the material properties. Now, here you should keep it in mind, what types of material property you should choose, properties you should choose in your analysis. So, to get that idea, first of all we should know what are the governing equation generally we are going to use in this analysis. So, you know that this welding residual stress analysis is a elastoplastic, what is called elastoplastic thermomechanical analysis, or you can say thermal mechanical analysis. So, this thermal mechanical you can write as thermomechanical analysis. So, you see, so for this elastoplastic thermomechanical analysis, generally by this we can find out this residual stress distribution in the weldment. So, it consists a thermal analysis, as well as it consists a mechanical analysis. So, in thermal analysis, what is the governing equation generally we are going to use, that we should know. So, in most of the thermal analysis, the main governing equation is Fourier heat conduction equation, that is very well known to you, and as it is a welding is a transient phenomena. So, here we should use transient Fourier heat conduction equation. So, transient Fourier heat conduction equation for a isotopic material, how it look like, we know del 2 T by del x square plus del 2 T by, for 3 dimensional case I am just showing del y square plus del 2 T by del z square. This will be equal to your rho c by k, you can say del t by del t. So, here you see, here our output is temperature. We want to find from thermal analysis what are the things required to do. From thermal analysis we have to find out temperature. So, this is the governing equation we know. Here generally we are using some extra heat, that means that is the load of thermal analysis. That heat is coming from electric arc, if it is a electric arc welding. If it is some other welding technique, is a laser beam technique, then laser power will be the load over there. So, if it is electron beam welding process, there will be electron beam power. So, that we show here our output is T. So, to find out this T in this equation itself, we can see what are the different types of material property are required. So, in a particular analysis, what should be the material property there, that you can get from that governing equation. So, in material property, so after modeling we have to go for material property. So, for material property, what should be the thermal material property? One is rho is called density, C is called specific heat, and K is called thermal conductivity. It is for a, if this material is isotopic in nature, then this K is constant through every direction, C is constant through every direction. That is why here I have taken a constant K. Okay. If it is different in different direction, then in this equation it will be different. So, what should be the input property there in thermal analysis? We have to use this material property. Now, in mechanical analysis, what is the basic governing equation generally we use? We know stress-strain relationship, that is stress is proportional to strain, where we can say stress equal to E into epsilon, that means Young modulus into epsilon. So, one parameter is required, that is called. So, this is in mechanical analysis. What should be the material property? First one is Young modulus, Young's modulus. So, as it is a 3-dimensional case, so in Young modulus this stress is dependent on Poisson's ratio also. So, there will be required Poisson's ratio. Now, here as it is a elastoplastic phenomena, that is why we have to consider there some yield criteria. Generally, in case of mild steel, the most appropriate yield criteria in case of welding analysis is von Mises yield criteria. What it is called? Von Mises, or you can say von Mises yield criteria. So, yield criteria generally is generally used for mild steel types of thermomechanical analysis in case of welding. So, in von Mises yield criteria, there you have to define yield stress. So, another material property required in this thermomechanical elastoplastic, as it is a elastoplastic analysis, that is why you have to define this yield stress. So, what are the material property we have to use? Young modulus, Poisson's ratio, yield stress. Now, here we are generally in case of mechanical analysis, we are using temperature as a load, correct? We are using temperature as a load, this you should keep it in mind. So, in mechanical analysis, we are using temperature is a load. So, this temperature generally in mechanical analysis, what it create? This temperature will create some thermal strain distribution, correct? So, that is why to define this thermal strain, depending upon this thermal strain, a stress strain pattern will be developed, correct, in this weldment. So, to define this thermal strain, what are the other properties required? So, we know thermal strain, generally thermal strain, let us E t, I am representing thermal strain. E t can be represented as what? E t can be represented as alpha into delta t. That means, this is the temperature difference, and this is called alpha is called thermal expansion coefficient, thermal expansion coefficient. So, what are the material property required over there? So, material property required in case of thermal analysis rho C k, whereas in mechanical analysis it is Young modulus, Poisson's ratio, then yield property, and another important property is thermal expansion coefficient alpha. This you should keep it in mind. So, once you go for doing any types of analysis, first of all you should know what are the analysis you are going to do. So, for that what are the boundary condition you are going to use. So, based on this boundary condition and what happens, what are the governing equation you are going to use, based on this governing equation we have to define this input material property, what I am telling, understand. So, that related things only here we are discussing. So, this thermomechanical analysis we can do sequential thermomechanical analysis first, that means sequential means first thermal analysis, then mechanical analysis, or we can do it by coupled thermomechanical analysis. Coupled thermomechanical analysis means at a single time we can do this thermal and mechanical analysis together, that means is coupled with one another. So, we can do this thermomechanical analysis both the way, one is sequential way, that means first of all we have to do thermal analysis, after that this thermal load we have to use in mechanical analysis, there generally we have to apply the boundary condition like what should be like, especially in welding thermomechanical analysis, there we use rigid body boundary condition. Okay, this you should keep it in mind. Now, here generally these things is described here in details, like after this importing all material property we have to apply the load, that load we can apply by distributed load or volumetric types of heat distribution also, because in case of welding there is a volume of molten material generally deposited over the line of the welding, correct. So, there we can use volumetric heat source distribution. So, that for that there are different types of models are there. Generally for 2-dimensional case, Gaussian heat distribution is a popular heat source model in welding. For 3-dimensional case, there is popularly used Goldak double ellipsoidal formula. This you just keep it in mind. So, I am not going in detail to describe all these things, because it will take lot of times, that is why just telling the name. So, for 2D case you can use Gaussian distribution, just here I am just writing Gaussian distribution types of heat source. For 3 dimensional case you can use Goldach double ellipsoidal heat source, or you can develop your own volumetric heat source. This is a volumetric heat source, this is a surface heat flux model. This is very popular one. So, once you go through this, you will go through the literature by typing this name, you will get all the information from there. So, that is why first of all we have to develop the heat source model, and we have to apply this heat source model over this welding region. After that, we have to apply the boundary condition. In case of thermal analysis, one is called initial condition, another one is called boundary condition. Initial condition of this thermal analysis will be when the heat source is not start to move. At that time, whole plate temperature here should be your atmospheric temperature. You can say T0, T equal to T0, when time T equal to 0, because it is a transient analysis, because here is a time varying, that means heat source heat is varying with time. So, it is a transient phenomena, that also you should keep it in mind. Okay. When time T equal to 0, then this is the things, and another boundary condition, this is called initial boundary condition, that means time T equal to 0, whole plate side type temperature is T0. Now, another 2 boundary conditions which are popularly used in welding, one is called convection, Newtonian convection of cooling boundary condition, another one is called radiation boundary condition. So, what is Newtonian convection of cooling boundary condition? Heat loss due to convection, this unit is generally watt per meter square, you can say, per unit area. This we can write as heat flux into T minus T0. Another one is radiation heat loss boundary condition, we can use, this is equal to sigma into emissivity, this Stephan-Boltzmann, this is called Stephan-Boltzmann constant, this epsilon is called emissivity, this is generally T to the power 4 minus T0 to the power 4. So, these are the 2 popularly used boundary conditions generally used, this unit also watt per meter square. Okay. So, these are the 2 popularly boundary conditions generally used in thermal analysis. So, after that we have to solve this problem. After applying the load and applying boundary condition, we have to solve this thing. So, by this we can get the entire plate surface temperature distribution. Okay. So, throughout the entire plate, top surface, bottom surface, internally, everywhere, what should be the temperature distribution with time, that we can get. That temperature distribution we have to take as input in a structural analysis, that I am showing here. Okay. So, in a structural analysis, again we have to define the boundary condition. So, the boundary condition, because in a structural analysis we have to generally position the plate in such a way it should not disturb. That is why what happens here, we can use rigid body boundary condition. One, we can use simply supported boundary condition. So, different types of boundary condition are there. So, depending upon this position of fixing the plate, we can define our boundary condition. So, after applying boundary condition, we have to apply this temperature, whatever the temperature we are getting from thermal analysis, this temperature we have to use as a load here. This temperature also in a structural analysis also it is a time varying temperature, correct. So, what the entire time, how this expansion contraction phenomena is taken place, once we apply all these boundary condition and material property together, then what happens, we can get the residual stress distribution pattern over the entire welded specimen. So, these are the different steps which are commonly used to predict the temperature distribution and residual stress distribution on a weldment. This you should keep it in mind. So, these are the references which I followed for these lectures. Thank you.